Hello there, and welcome to my channel, where we take the most mind-bending concepts in the universe and explore them at a pace that won't keep you tossing and turning all night. Tonight, we're diving into something that sounds like pure science fiction, but is actually happening all around us right now. Something so fundamental to reality that, without it, your GPS wouldn't work, satellites would drift hopelessly off course, and the very fabric of the cosmos would unravel before our eyes. The foundation of time dilation rests on one of the most profound insights in all of physics. The speed of light in a vacuum is constant for all observers, regardless of how fast they're moving. This might seem like a simple statement, almost boring in its technical precision, but this constancy is what makes time dilation not just possible, but inevitable. Think about it this way. If you're driving down a highway at 60 miles per hour and you throw a ball forward at 20 miles per hour, that ball travels at 80 miles per hour relative to the road. Speeds add up in our everyday experience, but light doesn't behave this way. Whether you're standing still or racing through space at 90% the speed of light, light always passes you at exactly the same speed. Always. This cosmic speed limit creates a profound puzzle. If light always travels at the same speed, no matter how fast you're moving, then something else must give, and that something is time itself. As you approach the speed of light, time slows down for you relative to observers who aren't moving as fast. The mathematics is elegant, the implications are staggering, and the experimental evidence is overwhelming. Einstein's equations, known as the Lorentz transformations, provide the precise mathematical framework for calculating these effects. The faster you move through space, the slower you move through time. At everyday speeds, the effect is so tiny as to be negligible. But as velocities approach the speed of light, time dilation becomes increasingly dramatic, theoretically approaching infinite dilation at light speed itself. This isn't just theoretical physics confined to dusty textbooks and university lectures. Time dilation is happening around you right now, in ways both subtle and profound. Every time you check your phone's GPS to find the nearest coffee shop or navigate through an unfamiliar city, you're relying on satellites that must constantly correct for time dilation effects. GPS satellites orbit Earth at about 14,000 miles per hour, and at that speed, their onboard clocks run slightly faster than identical clocks on the ground due to the weaker gravitational field they experience. But they also run slightly slower due to their high velocity. The net effect requires that satellite clocks be adjusted by about 38 microseconds per day. That might sound insignificant, but without this correction, your GPS would be off by miles within hours, making navigation completely useless. The engineers who designed the GPS system had to account for Einstein's seemingly abstract theories to create a technology that billions of people now take for granted. Every successful GPS calculation is a quiet confirmation that time really does bend and stretch according to the laws of relativity. But velocity isn't the only thing that affects the flow of time. Einstein's later work, his general theory of relativity published in 1915, revealed that gravity also influences time's passage. This gravitational time dilation occurs because massive objects literally warp the fabric of spacetime itself, creating curves and distortions that affect how time flows. The stronger the gravitational field you're in, the slower time moves relative to someone in a weaker field. This means that time passes slightly more slowly at sea level than it does on a mountaintop. The difference is incredibly small, measured in billionths of a second, but it's real and measurable with sufficiently precise instruments. We're talking about time dilation, the extraordinary phenomenon where time itself can stretch and compress like taffy, where seconds can become minutes, minutes can become hours, and in the most extreme cases, hours can become decades. It's a concept that challenges everything we think we know about the steady tick-tock of existence. Recent experiments have pushed these measurements to extraordinary levels of precision. Scientists at Gila, using ultra-precise atomic clocks separated by just a millimeter, have detected gravitational time dilation at the smallest scale ever measured. They collected 90 hours of data to achieve readings 50 times more precise than any previous similar measurement, opening new windows into the fundamental nature of reality itself. These cutting-edge experiments aren't just academic exercises. They're probing the intersection between Einstein's classical relativity and quantum mechanics, potentially revealing new physics at the boundary where our two most successful theories meet. Some researchers are even exploring quantum time dilation, where quantum effects beyond Einstein's original theory create additional corrections to our understanding of temporal flow. The precision of modern atomic clocks has reached levels that would have seemed impossible just decades ago. These remarkable devices can now detect time dilation effects over distances shorter than the thickness of a human hair, revealing that even at the smallest scales, Einstein's insights continue to hold true. As we venture deeper into the mysteries of time dilation, we'll explore how these effects become truly dramatic in the extreme environments found throughout the cosmos. Near black holes, where gravity reaches incredible intensities, time can slow to a crawl relative to distant observers. We'll journey to these exotic regions, where the very notion of simultaneity breaks down, and time itself becomes a dimension as curved and twisted as any roller coaster. We'll also examine the famous twin paradox, where space travel at near light speeds could allow one sibling to age only months, while their Earth-bound twin grows old over decades. It's a scenario that transforms time travel from science fiction into scientific possibility, limited only by our current technological capabilities. And we'll discover how cosmic phenomena, from the decay of particles in Earth's atmosphere to the light from distant supernovae, provide natural laboratories for studying time dilation on scales that dwarf any earthly experiment. But perhaps the most dramatic examples of time dilation occur in the most extreme environments the universe has to offer, places where gravity becomes so intense that it fundamentally reshapes the very nature of temporal experience. Let's drift toward one of these cosmic monsters, a black hole, where Einstein's predictions reach their most spectacular and mind-bending extremes. Imagine approaching the event horizon of a stellar mass black hole, that invisible boundary beyond which nothing, not even light, can escape. As you fall toward this point of no return, something extraordinary happens to time itself. From your perspective, everything seems normal. Your watch ticks at its usual pace, your thoughts flow at their regular rhythm, and the passage of time feels entirely familiar. But to an observer watching from a safe distance, your descent takes on an almost mythical quality. As you approach the event horizon, you appear to slow down, your movements becoming increasingly sluggish. Your watch, visible through a powerful telescope, seems to tick more and more slowly. The light you emit becomes redder and dimmer, stretched by the immense gravitational field. To that distant observer, you appear to freeze just at the boundary, your image growing fainter and fainter but never quite crossing over, suspended there for what seems like eternity. Now I should warn you, this journey through the warping of time might be just fascinating enough to keep you awake pondering the mysteries of spacetime. But if that happens, well, at least you'll drift off with your mind expanded by one of the universe's most elegant secrets. This is gravitational time dilation pushed to its absolute extreme, where the curvature of spacetime becomes so severe that time itself appears to nearly stop. The mathematics are precise and unforgiving. Close to a black hole, where gravity's pull becomes monumentally strong, the time dimension gets compressed and stretched in ways that challenge our deepest intuitions about reality. Now, you might have seen dramatizations of this effect in films, perhaps the water planet sequence in Interstellar, where a few hours, on a world orbiting close to a massive black hole, correspond to decades passing for observers farther away. While this scenario captures the essence of gravitational time dilation, the actual physics involved are both more nuanced and more constrained than Hollywood might suggest. In reality, achieving such extreme time differences would require incredibly specific conditions. The planet would need to orbit perilously close to the black hole's event horizon, far closer than any stable orbit could realistically maintain. The tidal forces alone would likely tear apart any solid world long before such dramatic time dilation could occur. But the underlying principle remains sound. Gravitational fields can indeed create substantial differences in the flow of time between different locations. The beauty of studying black holes lies not just in their extreme nature, but in how they serve as natural laboratories for testing Einstein's theories under conditions impossible to replicate on Earth. When we observe matter spiraling into these cosmic giants, we're watching time dilation play out on scales measured in solar masses and light years. But you don't need to journey to a black hole to experience the wonder of gravitational time dilation. It's happening right beneath your feet, right now, as you listen to these words. The atoms in your toes are experiencing a slightly stronger gravitational field than the atoms in your head, and therefore time is passing just a tiny bit more slowly for them. The difference is unimaginably small, but it's real and measurable with the right instruments. This realization leads us to one of the most profound insights about our universe. Time is not separate from space, nor is it independent of matter and energy. Instead, time is woven into the very fabric of spacetime. That four-dimensional tapestry that Einstein showed us underlies all of reality. Mass and energy tell spacetime how to curve, and the curvature of spacetime tells matter how to move and time how to flow. Recent advances in atomic clock technology have allowed scientists to measure these effects with unprecedented precision. Researchers can now detect gravitational time dilation over vertical distances of just a few centimeters, opening new possibilities for studying fundamental physics. These ultra-precise timepieces are so sensitive that they can detect the gravitational effects of objects as small as a person walking past the laboratory. Such precision has practical implications beyond pure research. Future navigation systems might rely on networks of these quantum clocks, creating a new kind of GPS that could work in environments where satellite signals can't penetrate. Underground mining operations, deep ocean exploration, and even interplanetary missions could benefit from this next generation of time-based positioning technology. The story becomes even more fascinating when we consider how time dilation affects the very particles that make up our universe. High-energy cosmic rays, particles accelerated to nearly the speed of light by violent cosmic processes, regularly demonstrate time dilation as they journey through space and Earth's atmosphere. Before we begin bending time together, I'd love to know where in the world you're listening from and what time it is in your corner of the universe right now. Are you settling in for the night in London at midnight? Or perhaps it's a quiet afternoon in Tokyo where you're stealing a moment of wonder? Drop a comment and let me know. Take muons, short-lived particles created when cosmic rays collide with molecules high in our atmosphere. Under normal circumstances, these particles decay so quickly that they shouldn't survive the journey to Earth's surface. Their natural lifetime is measured in microseconds, far too brief to travel the dozens of kilometers from their birthplace to sea level, even at nearly the speed of light. Yet muons reach the ground in abundance, raining down on us constantly in a gentle shower of cosmic particles. How is this possible? Time dilation provides the answer. From our perspective, the rapidly moving muons experience time more slowly, effectively extending their lifetimes and allowing them to complete their atmospheric journey before decaying. This phenomenon has been measured with exquisite precision in particle accelerator experiments. Scientists can create muons in the laboratory, accelerate them to known velocities, and directly observe how their decay rates change according to Einstein's predictions. The agreement between theory and experiment is so precise that it leaves no doubt about the reality of time dilation. These same principles apply to all fundamental particles. In the giant accelerators that probe the deepest secrets of matter, particles routinely travel at velocities where time dilation becomes a crucial factor in experimental design. Without accounting for these effects, our understanding of particle physics would be fundamentally incomplete. The implications extend beyond individual particles to the very structure of atoms themselves. When we peer into the quantum realm where electrons orbit atomic nuclei, time dilation effects, while tiny, contribute to the precise energy levels that determine how atoms interact with light. These quantum corrections to atomic clocks represent the cutting edge of our understanding, where Einstein's classical relativity meets the strange world of quantum mechanics. Some researchers are now exploring what they call quantum time dilation, where the probabilistic nature of quantum mechanics creates additional subtleties in how time flows for quantum systems. These effects push our theoretical understanding into uncharted territory, where the concepts of time and measurement become intertwined in ways that challenge our most basic assumptions about reality. As we continue our gentle journey through the landscape of time dilation, we'll discover how these principles play out on the grandest scales imaginable, in the expansion of the universe itself, and in the light that travels to us from the most distant galaxies. We'll explore how time dilation not only shapes individual experiences, but weaves through the entire cosmic story, from the first moments after the Big Bang to the ultimate fate of all matter and energy. The cosmos itself provides us with the most spectacular demonstrations of time dilation, written across scales so vast they dwarf our earthly experiments. When we gaze up at the night sky through a telescope, we're not just seeing distant stars and galaxies, we're witnessing time dilation in action on a cosmic stage. Consider the light from a distant supernova, one of those brilliant stellar explosions that can outshine entire galaxies for weeks or months. When astronomers observe these cosmic fireworks, they notice something remarkable. The light curves, those graphs showing how the supernova brightens and then fades over time, appear stretched out when the explosion occurs in a galaxy billions of light years away. This isn't because distant supernovas are inherently different from nearby ones. Instead, we're seeing cosmological time dilation in action. The expansion of the universe itself creates a kind of time-stretching effect, where events in the distant cosmos appear to unfold more slowly from our perspective here on Earth. It's as if the universe is playing an enormous slow-motion movie of its own history. If you enjoy these gentle explorations of cosmic mysteries, please consider giving this video a like and subscribing to join our community of curious minds seeking peaceful paths to knowledge. This effect becomes more pronounced the farther back in time we look. The most distant galaxies we can observe, those whose light has been travelling toward us for over 13 billion years, show us the universe as it existed when it was just a fraction of its current age. And in those ancient cosmic neighbourhoods, everything appears to be running in extreme slow motion, processes that would normally take days seeming to stretch across weeks when viewed from our modern vantage point. It's a humbling reminder that our perception of time is intimately tied to our place in the cosmic story. We're not neutral observers watching events unfold. We're participants in the grand expansion, carried along by the stretching of space-time itself. Every photon that reaches our eyes has been influenced by the expansion of the universe during its journey, arriving redshifted and time-dilated, bearing the subtle signature of cosmic evolution. This cosmic time dilation also affects our understanding of the early universe. When we observe the cosmic microwave background, that faint afterglow of the Big Bang, we're seeing radiation that was emitted when the universe was only about 380,000 years old. But because of the universe's expansion, the timescales we observe in that ancient radiation are stretched compared to what they would have been for observers living in that distant epoch. The phenomenon extends to gamma-ray bursts, those brief but incredibly energetic flashes that occur when massive stars collapse or neutron stars collide. These events, among the most powerful explosions in the known universe, provide natural laboratories for studying time dilation across cosmological distances. The duration and intensity patterns of these bursts carry the fingerprints of relativistic effects, allowing scientists to test Einstein's theories on scales spanning billions of light years. But perhaps the most poetic aspect of cosmic time dilation is how it connects us to the deep history of the universe. Every time we look at a distant star, we're seeing it not as it is now, but as it was when that light began its journey toward us. The farther we look, the farther back in time we see, and the more stretched and slowed those ancient processes appear. This creates a strange paradox of cosmic observation. The universe appears to be running slower in the distant past, yet from the perspective of observers living in those ancient times, their universe would have seemed perfectly normal, with time flowing at its usual pace. It's only from our modern vantage point separated by billions of years of cosmic expansion, that we see this temporal stretching effect. The mathematics underlying these observations are elegant in their simplicity. The redshift we observe in distant galaxies, that stretching of light toward longer, redder wavelengths, is directly related to the time dilation we see in cosmic events. Both effects arise from the same fundamental cause, the expansion of spacetime itself, creating a beautiful unity between observations of light and measurements of time. Modern space-based telescopes like the Hubble Space Telescope and the James Webb Space Telescope have allowed astronomers to study these effects with unprecedented precision. By observing thousands of distant supernovas and other cosmic events, scientists have been able to map out the expansion history of the universe and confirm that time dilation behaves exactly as Einstein's equations predict, even on the largest scales imaginable. These observations have also led to one of the most surprising discoveries in modern cosmology, the realization that the expansion of the universe is actually accelerating, driven by a mysterious force called dark energy. This acceleration affects the time dilation we observe from distant objects, creating subtle but measurable changes in how cosmic events appear to unfold over time. So, take a deep breath, let your shoulders relax, and prepare to discover how Einstein's most revolutionary insight continues to shape every moment of your existence, even as you lie there listening to my voice. The study of cosmic time dilation has practical implications as well. Future space missions to other stars would need to account for these effects when planning communications with Earth. A message sent from a spacecraft traveling at a significant fraction of the speed of light would arrive time dilated, with the duration of the transmission stretched compared to what was sent. Even more intriguingly, some theoretical physicists have proposed that advanced civilizations might use time dilation as a form of cosmic engineering, deliberately placing themselves in regions of strong gravitational fields or traveling at high velocities to effectively travel into the future relative to the rest of the universe. While such scenarios remain firmly in the realm of speculation, they illustrate the profound ways that time dilation could potentially be harnessed by sufficiently advanced technology. The effects we observe in distant galaxies also provide crucial tests of general relativity under conditions that can never be replicated in terrestrial laboratories. The gravitational fields around supermassive black holes at galactic centers, the extreme energies present in gamma-ray bursts, and the vast scales of cosmic expansion all create natural experiments that probe Einstein's theories in ways that continue to astound researchers. As we peer deeper into space and further back in time with each new generation of telescopes, we're effectively conducting an ongoing experiment in cosmic time dilation. Each observation provides another data point in humanity's growing understanding of how time behaves throughout the universe, from the smallest quantum scales to the largest cosmic structures. This cosmic perspective on time dilation reveals something profound about the nature of reality itself. Time is not a universal backdrop against which events occur, but an integral part of the cosmic story, woven into the very fabric of space-time and shaped by matter, energy, and the expansion of the universe itself. We are not separate from this cosmic dance of time and space. We are part of it, our very existence dependent on the delicate interplay of forces that govern how time flows throughout the cosmos. The gentle rain of cosmic particles continues to fall around us even now, each one a tiny messenger carrying the signature of time dilation from its high-energy birth in some distant cosmic accelerator. And as we drift towards sleep, we can take comfort in knowing that we are intimately connected to these vast cosmic processes, our own experience of time shaped by the same fundamental forces that govern the behavior of galaxies billions of light-years away. The journey through time dilation becomes even more intimate on the most personal level when we consider how it might affect human experience. Imagine, if you will, the profound implications of the famous twin paradox, where the passage of time itself becomes a character in a deeply human story. Picture two siblings, born on the same day, growing up together, sharing the same childhood memories and dreams. One becomes an astronaut, drawn by the call of distant stars, while the other remains on Earth, perhaps becoming a teacher or a gardener, someone who finds wonder in the everyday rhythms of terrestrial life. The day comes when the space-traveling twin embarks on a journey to a nearby star system, traveling at velocities approaching the speed of light. Picture this. You're standing on a train platform watching two identical clocks. One clock sits peacefully on the bench beside you, ticking away the seconds in perfect rhythm. The other clock is mounted inside a train that's approaching the platform at tremendous speed, faster than any train has ever traveled, racing past at a significant fraction of the speed of light itself. During the voyage, both twins experience time in their own reference frames as perfectly normal. The Earthbound twin watches seasons change, celebrates birthdays, perhaps has children and grandchildren. Meanwhile, the traveling twin experiences the same subjective flow of time aboard the spacecraft, watching stars wheel past, measuring the same heartbeats, breathing the same rhythm of seconds and minutes. But when the space traveler returns home, something extraordinary has occurred. The twin who journeyed to the stars has aged perhaps only a few years, while their earthbound sibling has grown old, their hair silver, their face lined with decades of experience. Time dilation hasn't just been a theoretical concept, it has written itself across their lives in the most tangible way possible. This isn't science fiction anymore, it's a genuine possibility within the framework of known physics. The mathematics are precise and unforgiving. At 90% the speed of light, time dilation becomes dramatic enough that a year of travel time corresponds to more than 2 years passing on Earth. At even higher velocities, approaching 99% of light speed, the effects become more extreme still. Current technology limits us to much more modest time dilation effects. Astronauts aboard the International Space Station, orbiting at about 17,500 miles per hour, experience time dilation of only a few milliseconds during their typical 6-month missions. Cosmonaut Sergei Krikalev holds the record for the most time dilation experienced by a human being, having gained about 20 milliseconds of relative time during his cumulative space missions. While these effects are tiny by everyday standards, they represent genuine differences in the passage of time. Krikalev has literally travelled further into the future than anyone else in human history, even if only by the breadth of a few heartbeats. It's a reminder that time travel isn't just possible, it's something we're already doing, albeit in the most modest way imaginable. The technology required for dramatic time dilation effects remains beyond our current capabilities, but the physics provides a clear roadmap. Spacecraft capable of sustained acceleration at comfortable levels, say 1 Earth gravity, could theoretically reach velocities where time dilation becomes significant over the course of a human lifetime. Such vessels could allow their passengers to journey across the galaxy while aging only decades, even as centuries or millennia pass on Earth. The psychological implications of such voyages boggle the mind. Imagine leaving Earth knowing that everyone you've ever known will be long gone by the time you return. The world you left behind would have transformed beyond recognition. Its languages evolved, its cities rebuilt, its entire civilization perhaps unrecognizable. You would become a time traveler, not by choice but by physics, carried forward by the inexorable mathematics of relativity. Yet there's something deeply beautiful about this connection between motion and time. It suggests that the universe has built into its very structure a kind of cosmic democracy. Time is not an absolute ruler dictating the same experience to all, but rather a flexible dimension that responds to how we choose to move through space. The faster we travel, the more we lean into the future, trading spatial velocity for temporal passage. Modern particle accelerator experiments continue to push the boundaries of our understanding, creating conditions where time dilation effects become routine and measurable. At facilities like CERN, particles are routinely accelerated to velocities where time dilation factors reach hundreds or even thousands. These experiments provide the most precise tests of Einstein's predictions, confirming his theories with extraordinary accuracy. In recent German experiments, researchers accelerated lithium ions to about 34% of light speed and used laser spectroscopy to measure time dilation with unprecedented precision. The results were nearly 5 times more accurate than previous measurements, providing some of the most stringent tests of special relativity ever achieved. Each such experiment adds another layer of confidence to our understanding of how time behaves under extreme conditions. As this impossible train whooshes by, something extraordinary happens. The clock inside the train appears to be running slower than the one beside you on the platform. Not broken, not malfunctioning, but genuinely ticking at a different rate. Time itself is moving more slowly for that speeding clock, and this isn't an illusion or a trick of perception. This is time dilation, and it's as real as the ground beneath your feet. The techniques involved in these measurements represent marvels of experimental physics. Scientists must account for countless sources of error and uncertainty, from the thermal motion of atoms to the vibrations of the Earth itself. The fact that they can measure time dilation effects to such extraordinary precision speaks to both the elegance of Einstein's theories and the ingenuity of experimental physicists. But perhaps the most profound aspect of time dilation lies not in its exotic applications or extreme manifestations, but in how it reveals the deep interconnectedness of space, time, matter, and energy. These aren't separate aspects of reality existing independently, but facets of a unified whole, a four-dimensional tapestry where changes in one dimension inevitably affect the others. This unity suggests something beautiful about the nature of existence itself. We don't simply move through time, we participate in its creation. Every step you take, every breath you draw, every movement of your body creates tiny, imperceptible changes in the flow of time around you. You are not a passive observer of temporal passage, but an active participant in the cosmic dance of space-time. The implications extend far beyond physics into philosophy and even spirituality. If time itself is malleable, responsive to motion and gravity, then our everyday intuitions about permanence and change require careful reconsideration. The present moment, that knife edge between past and future, becomes not a universal constant but a deeply personal experience, different for every observer depending on their motion through space. As research continues, scientists are exploring ever more exotic applications of time dilation physics. Some theorists have proposed using rotating cylinders of ultra-dense matter to create closed time-like curves, regions where the geometry of space-time becomes so twisted that paths through time loop back on themselves. While such constructions remain firmly in the realm of speculation, they illustrate how seriously physicists take the possibility that time itself might be engineered and manipulated. Others investigate the quantum mechanical aspects of time dilation, exploring how the probabilistic nature of quantum mechanics might affect temporal flow at the smallest scales. These quantum time dilation effects represent the cutting edge of theoretical physics, where Einstein's classical relativity meets the strange world of quantum superposition and entanglement. And so, as we drift toward the quiet end of our journey through the elastic nature of time, we find ourselves back where we began, in the gentle recognition that every tick of every clock, every heartbeat, every breath is part of something far grander than we often pause to consider. Time dilation isn't just an abstract concept confined to textbooks and laboratories. It's the hidden rhythm underlying every moment of your existence. From the GPS guiding you home to the cosmic rays gently raining down from distant stars. Whether you're lying here now in the early hours of morning or settling in as evening falls, remember that you are swimming in an ocean of space-time, carried along by forces both gentle and profound. The universe continues its ancient dance around you, time flowing and bending in ways both subtle and spectacular. And perhaps that's the most beautiful discovery of all, that in a cosmos where time itself can stretch and compress, where simultaneity dissolves and clocks can disagree, we still find ourselves here together, sharing this moment, this breath, this quiet wonder at the elegance of it all. This remarkable phenomenon was first predicted by Albert Einstein in 1905 as part of his special theory of relativity, a theory that would fundamentally reshape our understanding of reality. Einstein realized that time isn't the universal constant we once believed it to be. Instead, time is flexible, malleable, and intimately connected to motion and gravity in ways that continue to astound us more than a century later. Sleep well, fellow traveler through space-time, and may your dreams unfold at just the right pace.